Okay, so in this section, we are looking at titrating a weak acid with a strong base, and there's a couple calculations that I'm going to have you do here. So notice that when we're looking at a weak acid, we need to have an equilibrium constant in addition to the molarity and the volume of the acid. So notice that they're saying that the strong base is what is going to be added to the acid that is in the Erlenmeyer flask, sort of like what you did with your simulation. So in this first section here, there is no base being added. So we're just looking at the concentration of the acid, and we need molarity. So molarity, if you remember, is moles per liter. So if they give you volume, you want to make sure you convert that to liters. So they say that we have 50 milliliters of the acid, and we're going to use that relationship eventually. So they set up an ice table where we have acid, and notice that initially we have no product, and at equilibrium we're subtracting the amount of equilibrium concentration from the original. So you want to add both of them together. And then we're going to set up an equilibrium expression. So notice it is x squared over 0.1 molar minus x. Now because it is a -5, it's a pretty small equilibrium. And we're going to get rid of minus x, and we're going to take the square root of both sides. So I want to take the square root of 1.8 times 10 to the -5th. And I'm going to take the square root of x squared over 0.1. So when I take the square root of 1.8 times 10 to the -5th, I get 4.24 times 10 to the -3rd. And I want to multiply that by 0.1. The square root of that is the square root of that is 0.316. And when we multiply those two together, we get 1.34 times 10 to the -3rd. So that is the hydrogen ion concentration. So I want to take the log of that, and when I take the log of that, I get 2.87, and it's negative. So remember, it's negative times a negative, which gives me a positive 2.87. Okay, so that is when there is no base added. Now the next scenario here, we are now adding 10 milliliters of base, and we need to look at moles. I don't know if you remember from my last video. We're going to take the molarity times volume to give us moles. And when we do that, we have 0.1 molar times 10 liters, or I'm sorry, 0.02. My pencil is not working great here. 0.01 liters. And when you do that, you get 1.00 times 10 to the -3rd moles. And that's the concentration, or the moles of hydroxide. Now if we do the same thing for the acetic acid, remember it's the same concentration, but we have 50 milliliters, so it's 0.05 liters. And when we do that, we get 5.00 times 10 to the -3rd moles. Okay, so when we subtract, remember all the hydroxide is going to react with the acid, so it's going to remove some of the acid. So we have 0 hydroxide because it's already reacted, and we have 4 times 10 to the -3rd for the acid. And then for the anion, or the dissociated acid, we have 1 times 10 to the -3rd. Now we need to go back into molarity in order to figure out the hydronium ion concentration. So we want to take 4 times 10 to the negative third moles and divide by the total volume, which is 60, because 10 plus 50 is 60, and make sure it's in liters. And when you do that, you get this value here. And then we want to do the same thing with the anion. And we're going to put, oops, sorry, its concentration is 0.06 liters. And that is equal to this value here. So we're looking at the equilibrium concentration, so we want to add those two values together. Notice that we're losing some of the acid, which makes sense because it reacted with the hydroxide. And we're assuming that all of the hydrogen ion that was in the new solution is as a result of the hydroxide ion. And then we have the anion plus X. Okay, so we're going to set up an equilibrium expression, and we're still using the same one, so 1.8 times 10 to the negative fifth. And we are going to assume that we can get rid of the minus X and the plus X because it's so small. Okay, so we're still going to set up the numerator, X times 1.67 times 10 to the negative second, and that's going to be over 6.67 times 10 to the negative second. Okay, so in this situation, we're not taking the square root of both sides because we don't have to. So 1.8 times 10 to the fifth times 6.67 times 10 to the negative second, that gives us 1.2 times 10 to the negative sixth, and we're going to divide it by 1.67 times 10 to the negative second, and then solve for X. Okay, so I get 7.19 times 10 to the negative fifth. That's my new X. And I want to take the log of that. And when I take the log of that, I get a negative 4.14. And obviously a negative times a negative gives me a positive. All right, so I'm going to have you do the next two and see how you do.